Chlorine. Based on the one further this way, who's bigger? Boron. Based on who's further down? Well, the silicon or the chlorine could be. See how there's a conflict? You will not have that. It'll either be a tie, and one thing will determine it, or both things will be telling you to pick this guy. Fair enough? Okay, I'm not going to give you a conflict. All right. Go back to our rubidium, strontium, and cesium. Look at the difference between the size of rubidium versus strontium and rubidium versus cesium. Which one do you think has a greater difference in size? The difference between these guys or the difference between those two? And that's the right answer because of the difference in energy levels. Does that make sense? So when we say there's a decrease in size, yes, there is. Is this as dramatic as a change in size going down? No, but it's still dramatic enough to definitely comment on it. Okay, it's not like, well, it's just not changing that much. No, it's changing enough to definitely comment on. Questions? Yep.
Right, you said the reasoning for strontium being larger than rubidium is because the...
It's not, it's smaller. Strontium is smaller.
Yeah, sorry, my bad, yeah.
Okay.
You said that the reason for that was because the effective nuclear charge is pulling the outer electron shell closer, or the outer electron...
Right.
Okay, got it.
Yeah. Well, here. What it is because the effective nuclear charge is increasing going across, and there's no change in the energy level as it relates, because we're on the same amount of energy level, that means F, which is from Coulomb's law, how good a hold the nucleus has. What I'm saying is, as you go across the period, the nucleus gets a better hold on its electrons, so it's able to draw them in more closely. Make sense? So far, so good? Okay, that's it for atomic size. Next one up. Ionic size. Ionic size, you'll be happy to hear, follows the same trends, okay? Follows the same trends. The ionic size follows the same trends that we see normally for atomic size as ionic size, as long as the charge does not change. As long as the sign of the charge does not change. So for instance, if I were to compare sodium versus sodium ion, how do you suppose they differ in size? What do you think happens to the sodium ion when it loses its electron? It gets smaller. Does that make sense? If you were to take, for instance, an Fe plus 2 ion and look at it, compare it to an Fe ion, the Fe is going to be smaller. Why? Why does the atom get smaller when it loses electrons? Well, every ion that's positively charged is going to be smaller than its neutral counterpart, always, for certainly this reason. There can be other reasons as well, but certainly this will be one reason. When an atom loses its electrons, there is a substantial decrease in electron-electron repulsion among the electrons remaining. Since there's a substantial reduction in electron-electron repulsion, the nucleus is able to draw and bring in the electrons that more closely together. The electrons repel one another. The nucleus is trying to hold them in as close to itself as it can, but that repulsion, limits just exactly how close those electrons can be brought in. If you decrease and remove some of that electron-electron repulsion by removing one of the electrons, that means that there's not as much electron-electron repulsion, the nucleus is going to be able to draw the electrons in a little more closely than before. And it's rather startling the amount of difference you can see. In fact, I'll show you a picture of one of them in just a moment. By the same token, if you have a positive, if you have an atom that gains electrons, so if you look at chlorine versus chlorine ion, when you add an electron to an atom, there's a substantial increase in electron-electron repulsion, which means that the electrons, because of that greater amount of electron-electron repulsion, the electron cloud swells, and it swells noticeably. So a negative ion is always going to be larger than its neutral counterpart. Now, this difference that I was talking about is pretty darn substantial to this point, guys. If you take a positive ion and a negative ion, if you're going to do lots of betting during the day, and we want to bet on which one's going to be bigger, the positive ion or the negative ion, bet on negative every time, because 98% of the time you're going to win. Is there exceptions to that? Well, yeah, if we pick a really, really big positive ion, let's say like cesium, a cesium ion, and then a really, really tiny negative ion like fluoride, okay, yeah, then the positive ion is probably going to be bigger than the negative. But that's it. I mean, for the most part, positive ions are always smaller than the negative ions. Questions? Okay. As long as the sign doesn't change, that means we'll see the same trends as before. It'll go from small to big. So if I gave you, for instance, potassium ion and rubidium ion, which one's bigger? Well, rubidium was bigger before, and it's still bigger again. Okay. If I go across, look at sodium ion. Let's go do rubidium ion again, and strontium ion. Which one's bigger? Rubidium. Well, rubidium was bigger before, and it's bigger again. Okay. If we go ahead and look at the negative ions going across, as you go across, again, fluoride ion versus chloride ion. Chloride was bigger before, so chlorine was bigger than fluorine, so chloride's going to be bigger than fluoride. Again, no difference, follows the same trends. If you're looking at, O-2 and F-, oxygen was bigger before, so oxide is bigger than fluoride. That hasn't changed. What happens is you go across, again, it goes from small to big. Try it again. Big to small. Unless there's a sign change. Give you an example. If I were looking at, say, GE plus 4 and AS minus 3. Well, normally between GE and AS, which one's bigger? Germanium is bigger. Okay, they're both in the same row. Germanium is going to be bigger. Okay, lies further this way. But now, because of the sign change, hands down, the arsenic's bigger. Arsenide, rather, is going to be bigger than the germanium ion. You guys understand? Questions? No? This is a picture that shows just how dramatically. You see the green? That's the neutral. See the orange? That's the same element, but in positive form. See how much of a jump it is? Over here, the yellow is neutral, the brown is the negative. Yeah, that's how much of a change. Noble gases, disregard them. When this table was made, they did not know how to measure them properly. They were measuring apples and oranges. What I mean by that is they'd measure the size of all the other elements while they were bound to other atoms. And then the noble gases were not bound to other things. They measured them differently. And so you'll see that the noble gases are big. They're not. They're actually small. So disregard this. This chart does not actually reflect it. But if you just want to see just how dramatic it is, I'll just pass this around real quick. What page is that, Matthew?
190.
190. Thank you. That's one. There we go. Okay. You guys think you have it down?
Yes.
Yeah? All right, fine. Try this one. Rank these in increasing order of atomic size. Rank those in increasing order of atomic size, or ionic size. So I want the smallest one first and then the biggest one. We're going to go from small to big. We have our answers?
Yes.
Yes?
Yes.
All right. Who wants to give me the answer? All right, Joe.
Aluminum ion, magnesium ion, and sodium
Use the small to the biggest.
ion.
It's that chip in my head working the wrong. Go left. I mean right. It's that chip again. Okay. How many agree with Joe? How many disagree with Joe? Well, that's too bad, because Joe's wrong. That's okay. I would have bet on Joe too, probably.
I just go for it.
So, give me the right answer. Yes, there is. Michael.
Is it magnesium is less than sodium and sodium is
Oh,
less
wait,
than
okay, it was get small to big.
small? Yes. Okay. Magnesium,
Magnesium,
sodium,
sodium,
aluminum.
aluminum. Okay. Don't tell me. Do you have an explanation?
No.
Then I won't even entertain it as a possibility. Kyle,
Is it just the opposite orbit that it's in right now?
do you have an explanation as to why?
Because it's all the same charge, so just more protons, like more.
You're saying sodium is the smallest, and then the aluminum,
And then
and the magnesium,
magnesium.
and then the aluminum.
No, that doesn't make sense.
Okay. Jacob.
Is it Na then aluminum then?
Okay, Na plus and what?
Then aluminum and then magnesium?
Do you have an explanation?
Yeah. So when the Na loses an electron, it loses its energy level.
There we go. The sodium, when it loses an electron, loses a full energy level. It loses at 3s electrons, so its outer energy level is now the second energy level. When the magnesium plus one ion, magnesium doesn't show up. In the laboratory, we can put a gun to its head and make it do anything. Okay? Normally in nature, right, Mg plus 2 does not exist. But in the lab, we can make Mg plus. Okay, so we can do Al plus as well. When they lose an electron, they don't lose an energy level as well. Does that make sense, guys? All right. Now, if I had given you this, Al plus 3, and Mg plus 2, and Na plus, what you normally would expect them to see, then hands down. Why? Well, because the sodium ion is losing one electron. These guys are all losing more electrons, so you're reducing the electron-electron repulsion even more. So they were already, sodium was already bigger than these guys to start off with, and you're reducing their electron-electron repulsion even more severely because they're losing more electrons, so that definitely would have been the right answer. So all of you who wrote, who agree with Joe, if this were the case, that would be the deal. Should we be able to do something like that on the test? I probably wouldn't throw this at you on the test. Yeah, I'm not going to throw that to you. I'm not going to throw that probably on the test. Yeah.
You don't have to wear with.
I might do that to an AP class. I'm not going to do it to you guys. All right. Listen up. We've covered enough information for you to start work on that worksheet. Okay, I'm not assigning it because we're not done yet. Okay, tomorrow we will finish this chapter. Yeah, tomorrow we finish this chapter. See you guys. That means I gotta get that bonding chapter into your hands. Okay, those of you not here tomorrow, make arrangements, do whatever you have to.
It's just me and Mike.
You were here for the right day. tomorrow's a little easier, okay? Because it just